Hello, everyone. We're going to go ahead and go over section 2.4, which is on the average rate of change of a function. So we've learned about functions, their graphs, how to get information from graphs. Now we're analyzing graphs again, but also the equations, because we want to know what is going to be the average rate of change, how fast, how slow is something changing, or an equation changing, things like that. So as an overview, functions are often used to model changing quantities. Since there is a relationship between x and y, we imagine that there is something changing in our function as probably time goes on or anything else goes on. So in this section, we'll learn how to find the rate at which values of a function change as the input variable changes. So we're seeing how the output changes as our input changes. So how does y change as x changes? Or f of x in this case, since we're using functions. So our average rate of change, as just to set up the idea here, we can say, let's say you're taking a trip to South Lake Tahoe from Reno, and you would drive about 90 miles in, let's say, 2 hours. So your average speed or rate of travel would be that 90 miles divided by the time that it took you to drive that. So 90 miles divided by 2 hours is 45 miles per hour. Even if you didn't necessarily drive 45 miles per hour the whole time, that was your average. We imagine that, through streets and maybe winding roads, you're going a little slower, but maybe on the freeway, you're going quite a bit faster than 45. So that's just our average. We said this was the average speed over our given amount of time. So our distance divided by time in that case. So to find the average speed between any 2 points during any sort of trip, you want to divide distance by time. So that's a real life example that you're probably somewhat familiar with, since I'm sure you all have traveled somewhere in your lives before. If you were like me, that annoying kid in the back of the car on a road trip saying, when are we going to get there? When are we going to get there? And things like that. So my dad would make me find the average rate of change so I could know when we would actually most likely get there. But all right, here we go. We have the average rate of change. This is the definition from the book. We have the average rate of change of the function y is equal to f of x, so just some function, between the values of x is equal to a and x is equal to b. So we have the two values a and b that are both x values. And this is going to be the change in y divided by the change in x. Or in other words, when we actually use a formula, the formula itself is f of b minus f of a divided by b minus a. So we have these x values a and b, our change in y, that f of b and f of a, that is your function evaluated at b and your function evaluated at a, divided by the actual values b minus a. So the average rate of change is the slope of the secant line between x equals a and x equals b on the graph of f. That is the line that passes through the points a, f of a, and b, f of b. So the secant line, this idea that we're introducing here, your secant line is an imaginary line that is drawn between 2 points. So our average rate of change would be the slope of that imaginary line. So it's just the straight line that goes through 2 separate points, and our average rate of change is the slope of that. So if we look at our image right here, we have our graph here, we have some function. Our average rate of change formula is given here. We see that we have the x values a and b, and their corresponding y values, f of a and f of b. So this dotted line is our secant line. That's our imaginary line that we drew. And so when we calculate our average rate of change, we're taking the difference of those y values and dividing by the difference of the x values. In this case, for average rate of change, it doesn't necessarily which you pick to be A or B. It doesn't necessarily have to be exactly in this order, as long as the formula stays the same. You can pick smaller values to be A and F of A, or B and F of B, or larger values to be B and F of B, or A and F of A. It doesn't matter as long as you keep the formula in the correct order. So let's go ahead and do an example. So for the function f of x is equal to x minus 3 squared, we want to find the net change and the average rate of change between the following points. A, we want to look at x is 1 and x is also 3, and B, we're looking at x equals 4 and x equals 7. We have an image here to go along with this. This is the function, the red curve here, that is our function x minus 3 squared. And these dotted lines are those secant lines that are representing the average rate of change between these points 1 and 3 and 4 and 7. The image doesn't really do anything for us other than just give us a nice visual. So we're going to go ahead and go over to our notes to actually calculate the average rate of change and the net change for each following points that we have here for our function. All right, so here we are. We have our function x minus 3 squared. We have part A, we're looking at our function between the x values 1 and 3, and B, we're looking at our function between the x values 4 and 7. So we also have here, I've written out the net change formula, which we learned in our previous section, f of b minus f of a, where a has to be less than or equal to b. Then we have our average rate of change, f of b minus f of a, divided by b minus a. If you notice something, the net change is the same as the numerator of the average rate of change. The only stipulation with the net change is that a has to be less than or equal to b. So if we solve for net change, we've essentially also solved for the numerator of our average rate of change. All we did was say that a had to be less than or equal to b. For average rate of change, it doesn't matter. A can be less than or greater than b. Either way, just remember you have to keep it in the same formula. It's the only stipulation there. Doesn't matter what x values you pick for the average rate of change, as long as the formula stays the same. But for net change, we say that a has to be less than or equal to b. Since we have to do both anyways, and net change is part of average rate of change, we're going to kind of combine and use little bits of shortcuts here in our problem. So when we pick A and B for part A, we're going to make sure that A is less than B. So since in our problem we have that x is 1 and x is also 3, those are our two x values, we're going to say A is 1 and B is 3. So when calculating our net change, we know what A and B are, so we want to know what f of A and f of B are as well. We say that f of A is going to be f of 1, and f of B is f of 3. So now we want to actually calculate these values. For f of 1, we're replacing x with 1 in our original function. Our original function was x minus 3 squared, so now we're going to have 1 minus 3 squared. 1 minus 3 is negative 2, and negative 2 squared is 4. Now we can do the same thing for f of 3. We replace x with 3, so we'll get 3 minus 3 squared. 3 minus 3 is 0, and 0 squared is 0. So when we want to calculate net change, which is f of b minus f of a, which in our case is f of, we're just going to write this out, f of 3 minus f of 1. This simplifies to 0 minus 4, which is negative 4. So our net change is negative 4. Now, we want to calculate the average rate of change here as well. So we'll have average rate of change. Our average rate of change was f of b minus f of a divided by b minus a. Well, if we keep the same things, a is 1, b is 3, then this function is really f of 3 minus f of 1 divided by 3 minus 1. So this is our function here, and we already know what f of 3 and f of 1 are because we already calculated that for net change. We even know what the numerator of this function is it's -4 because f of 3 minus f of 1 is -4. We're going to write it out anyway, but you can always use that shortcut. So f of 3, we said we know that was 0. F of 1 was 4. 3 minus 1 is 2. So we get -4 divided by 2, which is -2. So the average rate of change for our function between these 2 points is -2. So, all right, let's go ahead and do part B as well now, using everything that we know here. So starting with net change, once again, we want to make sure that A is less than B. So we have x equals 4 and x equals 7. So we're going to go ahead and say that A is 4 and B is 7. So A is 4, B is 7, and now we're going to calculate our net change. Just like before, we've got f of A and f of B, where f of A is f of 4 and f of B is f of 7. So now we can go ahead and fill these out within our function. So for f of 4, we're replacing x in our function with 4. We can see our function there. It's a little slow. All right, so we're replacing 4 in our function. So we'll have 4 minus 3 squared. 4 minus 3 is 1. So we have 1 squared, which is just going to be 1. Then f of b, we have f of 7. So we're replacing 7 within our function there. So we're replacing x. So we've got 7 minus 3 squared, which is going to be 4 squared. And 4 squared is 16. So our net change, our formula, f of b minus f of a, we've got f of 7 minus f of 3, f of 4, my bad, f of 4, there we go. F of 7 was 16, f of 4 was 1. So the net change is 15. All right, so now we know our net change. We want to compute the average rate of change. So we saw before that if we picked the same format here, that our answer was, for part A, it was -2. So we're going to go ahead and do both. We're going to show picking the same values as net change and then also picking opposite values to just show that it works either way. So this first one here, same as before, average rate of change. This is going to be f of 7 minus f of 4 divided by 7 minus 4. So f of 7 minus 4, we said that was 15, but we're going to write this out, 16 minus 1 divided by 7 minus 4, which was 3. 16 minus 1 is 15. And 15 divided by 3 is 5. So the average rate of change of our function between the x values of 4 and 7 is 5. So now that we've definitely verified this twice, we're going to go ahead and show that it doesn't matter what values to pick between A or B, as long as the format is the same. So we're going to write 4. We're going to say that A is 7 and B is 4. So we're switching A and B. So if this were the case, we would have f of 4 minus f of 7 divided by 4 minus 7. We kind of see how these numbers match. So the 4 is kind of above the 4, 7 is above the 7. That is always the key that you want to stick with. Doesn't matter which values you pick to be A or B, as long as they're kind of stacked on top of each other, like how we're looking at right here. That's going to be that key value there. We'll actually color these a little different. Oh, those are very dark. So we see those numbers match in that case. And we're going to see that it comes out the same. We said f of 4 was 1, f of 7 was 16. So we have 1 minus 16 divided by 4 minus 7, which is going to give us negative 3. So 1 minus 16 is negative 15 divided by negative 3. Those negatives cancel each other out. 15 divided by 3 is 5. So we see that it doesn't matter which points we pick for A or B when it comes to average rate of change. Our answer should be the same as long as we're following the same formula. This is not true with net change. You have to have A less than or equal to B for net change, but for average rate of change does not matter. So here's the proof of that. All right. That wraps up our first example here. So let's go on and head back over to our lecture. All right, so we just wrapped up example 1. Here again is that visual. So we saw that between the values of 1 and 3, we actually did have that negative slope. So we see that line is kind of going down. And we had a positive slope between 4 and 7. So we saw that line going up as well. So those were indicators on if we should have, negatives or positives for our answers. But all right, let's go ahead and move on to example 2. Here we go. So if an object is dropped from a high cliff or a tall building, the distance, which is in feet, it has fallen after t seconds is given by the function d of t is equal to 16t squared. We want to find its average speed or its average rate of change between 1 and 5 seconds. So we have a word problem here. We have this object that's being dropped. We have a function, and we know those time stamps that we're looking at. T equals 1 and t equals 5. So we're going to find our average rate of our average speed or average rate of change just the same. So let's go ahead and head on over to our notes. All right, so here we are. We have our function d of t, which is 16t squared. Our timestamps t equals 1 and t equals 5. And then we have our average rate of change function written there again. So our first step, as always, we want to identify or just pick what is going to be A and what's going to be B. Like we said before, it doesn't matter which one we pick to be A or which one we pick to be B. As a habit of mine, I tend to always just pick the lower number as A and the higher number as B. But if you want to go the other way around, remember, it works the other way. You should get to the same answer as long as your formula stayed the same. So let's go ahead. We're going to say that A is going to be 1 and B is going to be 5. So if we know that A is 1 and B is 5, we now want to know what's f of A and what's f of B. So we're going to go ahead and calculate those. F of A is going to be f of 1. So in our function, which is d of t, we don't even use f at this point. It's going to work the same. But if you want to replace it with d instead, you could do that as well. But so we have our function evaluated at 1. So 16t squared, we're going to replace 1 with t. So we're going to have 16 times 1 squared. 1 squared we know is 1. So we've got 16 times 1, which is still just going to be 16. All right. Then we have f of b. We said that b was 5. So we have our function evaluated at 5. Our function was d of t is equal to 16t squared. So we're going to plug in 5 for t. So we'll have 16 times 5 squared. 5 squared is 25. So we have 16 times 25 in this case, which calculators or brains, whichever ones you prefer, this is going to be equal to 400. So we have f of A and f of B, and we know what A and B are, so we can go ahead and plug this into our equation for our average rate of change. So we have f of b minus f of a divided by b minus a. F of b is 400, which actually, let's go ahead and write out real quick. This is going to be f of 5 minus f of 1 divided by 5 minus 1. f of 5 we said was 400, and f of 1 was 16, divided by 5 minus 1, which is 4. So we can go ahead, figure out 400 minus 16 is, or go down here, is going to be 384 divided by 4, which, if we want to use calculators, is 96. So we remember that our function was in feet. Our time stamps here were in seconds. So this final answer is in feet per seconds. The unit may not be incredibly important all the time, but helpful to know for word problems especially. But all right, that finishes up example 2. Let's go ahead and head back on over to our lecture. All right, so that was example 2, which we just finished up. And moving on, we have average rate of change, just some more information about it. We say if a function is increasing on an interval, remember we talked about increasing in our last sections. So if a function is increasing on a specific interval, the average rate of change between those 2 points will be positive. It is going up. Its rate of change is positive, so it's increasing. So we can associate increasing with positive rates of change. Increasing, getting bigger, more positive. So we can associate those kind of 2 positive attributes together. Then similarly, if a function is decreasing on an interval, your average rate of change between 2 points will be negative. So those values, they're going down, they're going kind of probably in the negative direction. So we can associate those 2 negative aspects together as well. So we have some images here. First one on the left, we say that if our function here is increasing, so it's going up as we're looking from left to right, our average rate of change is positive. Our slope is greater than 0 because our line is going upwards. Then on our right-hand side, we have our other graph. Our function here is decreasing, it's going down. Reading from left to right, since this line is a negative slope or a decreasing slope, our average rate of change has to be negative. So this is just another way that we kind of draw some information about average rate of change just by looking at a graph. We can automatically associate a function that's increasing with positive slope and a function that's decreasing with negative slope. It won't necessarily tell us exactly what the slope is, but it should give us an indicator as to what sign our average rate of change should have at the end. Let's go ahead and do our last example here. So we have example 3. The table below gives the outdoor temperatures observed by a science student on a spring day. Looking at the graph of the data in the table, find the average rate of change of temperature between the following times. So our picture here that we have, our graph, is just giving us a general idea between what times should we be expecting positive slopes and negative slopes, or positive or negative rates of change, things like that. But we're actually really mostly going to be looking at the table and the timestamps that we have. So for part A, we want to look at the rate of change of our temperature between the times of 8 and 9 a.m. We want to look at the average rate of change of temperature between 1 and 3 p.m. and also between 4 and 7 p.m. So here is our table here. We're going to go ahead, we're going to write down all the important information in our notes. So, the time and temperature at 8, 9, 1, 3, 4, and 7. But here we have all of those times and temperatures and the graph of what the temperature looks like throughout the day. So, all right, let's go ahead and head on over to our notes. All right, so here we have example 3 and all of its important information here. We're solving for the average rate of change. We have time and temperatures, and we're looking at the change in temperature between all of these different times. So, side note, if you notice that a lot of these times are underlined, my iPad's trying really hard to create events for them. So hopefully nothing pops up, but they have lines underneath them. It's fine. But all right, so one thing to notice here about our time and temperature is that our temperature depends on the time. We know that throughout the day, it's probably going to get warmer as time goes on. And then when it starts getting colder, we know that the time is, probably after the sun goes down, things like that. So we kind of get this like bell curve almost looking thing. So our temperature depends on time. So in our average rate of change, we have these values, you know, A and B, which are values of X. So for us, we can say that really time is X. And our temperature is going to be f of X. It's our function that depends on X. So really all we need to do is figure out what's A and what's B, and then we have all of the values that we need. So let's go ahead and start off with part A, 8 a.m. and 9 a.m. Let's go ahead and say that, you know, A is 8 and B is 9. So for us, we have that 8 a.m. At 8 a.m., the temperature is 38 degrees Fahrenheit, and at 9 a.m., the temperature is 40 degrees Fahrenheit. So in this case, when we go ahead and we write out our equation here, f of b minus f of a divided by b minus a, we say that a is 8, b is 9. So our function is f of 9 minus f of 8 divided by 9 minus 8. F of 9 is our temperature at 9 o'clock, and f of 8 is temperature at 8 o'clock. So if we know that the temperature at 9 o'clock is 40 degrees, f of 9 is 40. So we've got 40. And our temperature at 8 o'clock is 38 degrees, so f of 8 is 38. We've got 40 minus 38 divided by 9 minus 8, which is 1. And 40 minus 38 is 2. And 2 divided by 1 is just 2. So that would be our answer. Our average rate of temperature would be 2, and in this case, it would be degrees. So a positive 2 degrees is our average rate of change between the times of 8 and 9. So let's go ahead and do our next one. I'm going to erase these because we're going to do that again. So now we have between 1 p.m. and 3 p.m. So same thing as before. We're going to go ahead. We're going to pick A and B. Once again, doesn't matter which one you pick, just as long as the formula stays the same. I'm going to say that A is 1 and B is 3. So our function here needs to be f of 3 minus f of 1 divided by 3 minus 1. So now we need to find the temperatures at 3 o'clock and 1 o'clock. So at 1 p.m., our temperature was 62 degrees. And at 3 p.m., our temperature was 67 degrees. So our function f of 3 is the temperature at 3 o'clock, which is 67 degrees. Then f of 1 is our temperature at 1 o'clock, which is 62 degrees. Then it's divided by 3 minus 1, which is 2. 67 minus 62 is 5. And then we have 5 over 2. You can leave it as 5 over 2, or you can calculate its decimal value, which is 2.5. So that is our average rate of temperature between the time 1 and 3. We have a positive 2.5 degrees. So, all right, now let's go ahead and do our last one here. We have 4 p.m. and 7 p.m. These are p.m.s, they look a little funny. All right, we have 4 p.m. and 7 p.m. Let's go ahead, we'll switch it up. We'll say 4 p.m. is B and 7 is A. So we'll say B is 4, A is 7. Just to show again that it doesn't matter which one we pick, as long as the formula is correct, we should get the right answer. But so we have 4 p.m. and 7 p.m. So for our average rate of change here, we want to find f of 4 minus f of 7 divided by 4 minus 7. So we want to find the temperature at 4 p.m. and the temperature at 7 p.m. Our temperature at 4 p.m. is 64 degrees, and our temperature at 7 p.m. is 51 degrees. So we're going to go ahead and put those in for our function values. So f of 4, our temperature at 4 p.m. was 64 degrees. So we'll have 64 minus our temperature at 7 p.m., which was 51. So we have 64 minus 51 divided by 4 minus 7, which is -3. So our function 64 minus 51, that's going to be 13. And we're dividing by -3, which means that this whole thing is negative. So we have 13 divided by 3, which is negative, or -13 divided by 3. We can calculate this value in decimal, or we can leave it like this. But so in decimal, this is going to be -3. I wrote that wrong, sorry, -4.33. There we go. -4.33 degrees. So between the hours of 4 and 7, we saw decreasing temperatures. We saw that our average rate of change was a -4.33 degrees. So, all right, that wraps up example 3. Let's go ahead and go over back to our lecture. All right, so that was example 3. We can go ahead and move on. So just our last concept here, linear functions have constant rate of change. So the functions that we've been looking at have been non-linear. They are not lines. We've seen, parabolas, they're curvy, or just curvy functions in general. That's what we've been dealing with here. And we've been dealing with this because linear functions always have constant rates of change, which just means that they're not very interesting to solve for their slope, other than if you just do it once. So quick recall, a function of the form f of x is equal to mx plus b is a linear function with slope m and y-intercept b. So that's our slope-intercept form, y equals mx plus b. If a function has a constant rate of change, it has to be a linear function, and that's because the average rate of change of a linear function between 2 points is the constant m. So slope and average rate of change are the same thing. So if you have a straight line, you have a constant slope. The slope is never changing. And it's excellent, and you a lot of the time want to find the slope for linear functions, but only once, because it will be the same no matter what 2 values of x you choose that are on that line. You can pick -100 and +100, or -1, +1. The slope is always going to be the same. The average rate of change is always the same. So linear functions have that specific characteristic where they always have constant rates of change. The rate of change does not change at all between different values of x. So just a fact to move along here into our future sections. But all right, that wraps up section 2.4. So in summary, in section 2.4, we covered average rate of change and linear functions have constant rate of change. So all right, that wrapped up our section 2.4, and I'll see you in the next one.